Guys and gals, you've done great so far. You've tried your hardest to master one-dimensional kinematics, but guess what? 1D is so last week. It's time to step up to 2 dimensions. In order to do that, you're going to need to know something about a little thing in physics called vectors. So let's jump right in. You've actually been using vectors for some time already. Okay, let me show you an example of some vectors. Right there. Displacement, velocity, acceleration, force. Okay? Sometimes it's best to define something by comparing it, or not best, but useful to define something by comparing it to something else. I'm going to compare what a vector is to what something else called a scalar is. Okay? So look at these two lists here. You see displacement here on the right, and you see distance on the left. You see velocity on the right, you see speed on the left. You already know, we've already talked about how those two are related. They are similar but not the same. All right, what distinguishes them? Do you remember? Well, let me pull down a little further here and give you a few definitions. Okay, a scalar is defined as any quantity described completely by a magnitude only, right? By a size or amount. Think for a minute about your age. Do you ever say that you're 17 years old north? No, right? It doesn't make any sense. You don't need direction to completely describe age, right? So age is an example of a quantity that is a scalar because all it needs is a number to describe it completely, okay? However, on the other side over here, right, take, for example, a force, okay? Not only do we want to know how hard you're pushing something, right? We don't want to only know how hard you're pushing something, but we also want to know in which direction you're pushing. So, for example, this would be like 5 newtons, oops, this would be like 5 newtons east, for example, right? Okay? In other words, a vector is a quantity that needs not only a magnitude, but also a direction. Okay? And let's fix the spelling here, right? Direction. Right? All of these quantities over here, displacement, velocity, acceleration, they all need a direction to describe them completely. Okay? Remember, velocity would be like 60 miles per hour north. Okay? Whereas the speed would just be 60 miles per hour. Okay? So a vector are these quantities that need direction. Okay? Whereas scalars are just other quantities that all they need is a number. Okay, when working with vectors, especially on paper like you will, it's helpful to have a certain tool. Okay, it's going to make working with vectors a lot easier, and that tool is the arrow. Okay, we're going to use arrows to represent vectors. If you think about arrows, they have both magnitude, right, and we can just use the length of the arrow to represent the magnitude of a vector. All right, and then secondly, arrows also have direction. So if there's a vector, say again, the 60 miles per hour north, right, the velocity vector. We can draw an arrow up, okay, and say that that's going to be north, right? That's going to be a vector that represents a velocity of 60 miles per hour north, okay? So let's look a little more closely at magnitude. We like to pay attention to size, okay? So I'm going to draw a similar one here. Let's call this 60 miles per hour east. Okay? What do you think an arrow would look like that would represent another velocity? Okay, this velocity would be 30 miles per hour west. Okay? How would that arrow representing 30 miles per hour west look different? Okay, well, it's not too difficult, right? You're going to point it the other way, and you're going to have it be half the size. Okay, I didn't do that very scientifically, right? I didn't get the ruler out. But, you know, if, right, this might be, oops. Right, if on my ruler, okay, if this is 5 centimeters, right, then I'm going to make sure that this one here is going to be 10 centimeters. Okay, that's just called setting up a scale. Okay, that's just called setting up a scale. In this case, 1 centimeter equals 6 miles per hour, right? Because when I get 5 centimeters, 5 times 6 is 30, and 10 times 6 is 60, right? So I've basically set up the scale. Okay, now, as you know, vectors have both magnitude and direction. And let's talk about direction. Okay, so far direction's been pretty easy for us in 1D kinematics, right? We only have 2 choices. In 1D, we had relatively few choices, right? In the case of free fall, we might go up or down, okay, or right, left, for example, or perhaps north, south, right, or east, west, okay? But basically, we only had 2 directions, and so it's pretty easy to keep track of them, right? We used plus or minus, okay, that was it. So only 2 directions really in any given problem. Could be up, down, could be right, left. However, direction in 2D, if you think about it, right, you could have, yeah, you could be going to the right, or you could be going to the left, but you could also be going at an angle, right, at some angle. Any one of these arrows is a 2-dimensional vector. So how are we going to handle that? Well, we're going to have to use angles. And this is where your prior math knowledge is really going to help you. Okay, I'm going to show you with one vector 4 different ways to represent the direction of that vector. Okay, we're going to start with polar coordinates. Okay, in the polar coordinate system, if you remember from math, okay, and if you don't, we'll just learn it right now. In the polar coordinate system, we're going to take a circle and divide it up into 360 degrees. But we're going to start our counting right over here, okay? And we're actually going to go counterclockwise, right? 90, 180, around the circle like that, okay? Where these are degrees. And so this over here is 0 or 360 once you get all the way around the circle. All right, so let's look at this arrow right here that I've drawn, okay, this one. You can kind of see that it's between 180 and 270 degrees. To know exactly what it is, we'd have to know what this angle is right here. Okay, and I'm just going to tell you what it is. It's 30 degrees, right? And then the way that we would say the direction of this vector here, right, this vector in polar coordinates, we would start from our 0 line, which is right there, and we would go counterclockwise until we hit it. Okay, so if you look, we crossed 90, right, and then we did 180, and then we did 30 more degrees. In other words, this vector is at 210 degrees. Okay, that's one way to say the direction of this vector. Now, another way to do the same vector, okay, so I'm going to take the same vector again, but this time I'm going to go the opposite way. Okay, so again, I got 0. This is 90 here. I won't write it because it's in the way. 180. Okay, it's the same point there. But this time I'm going to go clockwise. Okay, I'm going to go clockwise around until I hit it. Okay, and if you think about that, right, you've got 90 degrees here, and then think about what this is right there, right? If this is 30 and that whole quadrant is 90, well then this must be 60, right? So I have 90 plus 60, that's 150 degrees, but notice I've gone the opposite way. How are we going to keep track of that? Exactly, we're going to do negative. So you have negative 150 degrees. So it's the same vector, I've just indicated its direction 2 different ways. Okay? All right, 2 more ways. It's called using the cardinal directions. You may not be familiar with that word, but you will be familiar with north, south, east, west, right, which is what the cardinal directions are. Okay, so instead of using the polar coordinates, we're going to use north, south, east, west, okay? And when you use the cardinal directions, the direction will always be at an angle less than 90. You just have to get it in the right quadrant. Okay, so you can see that our vector in this case is in the southwest quadrant. Again, this angle is 30 degrees. So the way we write this would be 30 degrees southeast of west. In other words, I used west as my reference line, and I went south of it, 30 degrees. Okay, so 30 degrees south of west. But just like in the case of polar coordinates, I can go the other way. Okay, I can come up from the south. So let's see what that looks like. Right, I've got the same directions here again, east, west, north up here, and south. Okay, maybe draw a little separation line here. This angle is still 30 degrees, but now I'm going to come up from the south. Okay, in other words, I'm going to come up from this direction. I'm sure you can see that this is 60 degrees, right? And so I could also write this as 60 degrees, I'll write it down here, 60 degrees west of south. Okay, in this case, I use south as my reference line, and I went west of it. So there you have it. 4 different ways to tell the direction of a two-dimensional vector. Okay, 2 ways using polar coordinates, right? And 2 ways using cardinal directions. All right. The thing to realize here is that all of these 4 answers are equivalent, right? They're 4 different ways of saying the same thing.